Hi, we are Group 11 and this is our final project video. These people are our group members. And this is the outline of the slides. We will start by describing our motivations of our topic. Next, using several sections to talk about how we implement this project. In the end, we will show our results after implementing and try to analyze. After that, there will be some appendix for something like GitHub link, reference, and contributions. So first is our introduction. How we choose this topic. In the beginning, we have thought of many ideas. However, many of them may be too hard for us, or some ideas may be occupied by other groups. However, suddenly we come up with one idea and found that almost no group doing the AI for medical field. Thus, we decide to choose AI applying to medical things. After selecting this, we think COVID-19 is the most influential disease and really is really a dangerous problem in our lives, and it affects us a lot. Therefore, we want to solve some problems about COVID-19. And after searching online, we decided to do a classification for COVID and non-COVID CT images. Why do we choose CT images? Because we think that CT images have more checks to different layers of our part in our bodies than just normal X-ray images. So we select CT images instead of normal X-ray ones. So after introducing our problems, let me talk about our methods. The first one is highlight features and ADA boost. The second one is VGG16, and the last one is Inception v3. We want to check whether these three existing classification models can be applied to this field to do the classification accurately. The next section is about related works of these methods. The highlight feature with AdaBoost. The most related work is homework 1, and in that homework we use OpenCV to load data, and the resolution of the detector is 19 multiply 19. And in our project we change that to 24 multiply 24 because the original paper of highlight features use this scale. And in our homework 1, our dataset including training and testing only 400 images in total. And in our project, we use about 1,000 images to do this. Although in homework 1, we use highlight feature with AdaBoost to classify face and non-face. And we usually see something using highlight features to be applied to detecting human face. But we still decide to use this method because we want to try to explore more and the different applications of this method. Furthermore, our topic is to do the classification, so we think that it's also okay for this classification method to classify other things like COVID-19 CT images.
When we were deciding on a topic, we had to come across this paper. This paper discussed the existing powerful CNN recognition modules, such as ResNet or VGG, particularly those located near the upright corner. These modules not only achieve above average accuracy, but also have a physically wide range of recognizable categories. Therefore, we decided to focus on VGG and inception V3. The second paper, which we found during our subsequent data search, is a more comprehensive paper that elaborates on the accuracy and module structure of various networks in medical image recognition. It has been a frequently referenced paper in our subsequent work. Moreover, it includes a prior comparison of the accuracy of different modules like ResNet 3, 34, and VGG 16 and VGG 19. Hence, we select two modules from there that show high performance in terms of data, namely Inception V3 and VGG. And these are the VGG structure, and this is the input type and resource and some analysis.
Next, let me introduce our dataset. Our dataset comes from Mendeley data. It consists of about 5,000 COVID and 2,500 non-COVID CT images. And we split the dataset randomly into train and test data with 7:3 ratio. Next is our baseline. Let's start at highlight feature part. Different from homework 1, our highlight feature detector resolution is 24 by 24. The input image is transformed to grayscale and the number of weak classifiers, which is T in the code, is 10. This is the same part as homework 1. As for VGG16 and Inception V3, here are our parameters. Epoch is 10. Input size is 299 by 299. Batch size is 32. Normalize the data by using mean equals to 0.485, 0.456, and 0.406, and standard equals to 0.229, 0.224, and 0.225. The numbers are ImageNet statistics. It may not fit our data perfectly, but the number won't be that different. VGG16 and Inception V3 are both convolutional neural networks. We will introduce their structure in main approach section. Next is our main approach. We send our data into three different models: highlight feature and the AdaBoost, which is Viola-Jones algorithm, VGG16 and Inception V3. Start with Viola-Jones algorithm. It uses highlight feature to get the features. Features are used to extract some useful information, like edges and lines. The value of the feature is the difference between the sum of the pixels within two regions. In order to calculate the pixels in a region, we transform our data into integral image. The formula of integral image is this. The value of current pixel is the sum of the pixels whose x and y are both not larger than the current pixel in the original image. After transforming into integral image, for example, we can calculate region D by 4 minus 2 minus 3 plus 1. Next is AdaBoost. This part is same as homework 1. First, we initialize the weight and starting the loop. For each loop, normalize the weights and chain weak classifiers. Next, choose the classifier with the smallest error. Then update the weights. Finally, get a strong classifier and save it. After this, we can evaluate our classifier with test data.
I'm going to introduce the description of the VGG architecture that we have used in this project. And VGG is a CNN architecture designed by the University of Oxford. As shown in the left this image, it consists of 5 blocks and 3 fully connected layers. The input image will be divided into RGB3 channels for training. The final output will be a tensor with 1,000 classifiers, and each classifier representing a specific category. For example, if I input a dog image, and this image will divide it into RGB3 channels and performing convolution, ReLU, max pooling, and fully connected layers. And finally, output a tensor with a high value in the dog category, allowing the module to classify this image as dog. And VGG has various types, as shown in the imagery. Although the number of convolution layers may vary, the overall structure consists of 5 blocks and 3 fully connected layers. And the VGG architecture we have used is biased towards the D-type. It's the same as the D-type, and which has 13 weighted convolutional layers, followed by 3 fully connected layers, totaling 16 layers. Other famous VGG networks like VGG19 correspond to the E-type, which has 19 weighted layers and so on. And regarding the earlier slide in this slide, it's worth mentioning that the max pooling operation visually appears to have the same depth and have the same depth as the subsequent convolutional layers in terms of size. However, in reality, max pooling simply performs filtering, so apart from reducing the width and height by half, the depth should remain the same as the previous block. So if the previous block is the 224 times 224 times 16 the max pooling will be 112 times 112 times 16 and the next convolutional layers will be 112 times 112 times 128. So this image is kind of different from our module architecture. And the specific operation of max pooling can be seen in the next slide, this page. And max pooling has two parameters, kernel size and stride. And kernel size determines the size of each scanning window, while stride determines the interval between each scanning window. For example, starting from 1, this location, since the current kernel size is 2, so max pooling will examine a 2 times 2 range, which is 1256, and the max value is 6, so the first output will be 6. And since the stride is 2, so next position to scan is 3, like equal to 1 plus 2. Therefore, the next set of numbers to examine is 3478, and the max value is 8, so the second output will be 8, and so on. Now, referring back to the previous image, we can observe that the convolution continuously reduces the size of input in this image. The first input will be 5 times 5, and the first convolution will reduce this size into 3 times 3, and so on. And to maintain the same size in each block of convolutional layers, VGG applies additional padding, which means copying the edge value until the size matches the original. In the middle hidden layers of the VGG architecture that we have used in this project, we have not made any modifications. It is important to note that VGG provides pre-trained parameters, which were obtained from a large collection of images and are statistically suitable for training images. We have also used this parameter during data normalization, where the three values in this represent the normalized value for the RGB3 channels based on the occurrence of color in the larger dataset. However, the impact of this normalization on training is not significant, so I won't go into further detail. And in this project, we will compare the performance of pre-trained and non-pre-trained modules to observe the difference between them.
Now, I would like to talk about the concept of Inception v3. Inception v3 is a deep convolutional neural network model that was developed by Google. It is designed for image classification and object recognition tasks. Inception v3 builds upon the original Inception architecture, introducing several improvements to enhance its performance and efficiency. And we start from the first level, we divide the Inception v3 into 5 stages. There are 3 modules and the original input and the output stage. And our output size is 299 times 299. And the main idea is module. Because of this module, the model are designed to capture more information at different levels of spatial granularity by using filters of various sizes. And this allows the network to learn both local and global features, improving its ability to recognize complex patterns in images. And in these 3 modules, one of the key advancements is the usage of factorization into smaller convolutions. Instead of applying a single large filter, the network uses a combination of smaller filters. Like figure 1, we can see this is 3 times 3. And the original architecture is 5 times 5. We replace it with 2 3 times 3 layers. And we use this to process the input. These replacements reduce the computational cost while preserving the representational power of the network. Another important technique employed in Inception v3 is dimensionality reduction, to reduce the dimensionality of features maps and make the network more efficient. 1 times 1 convolutions with smaller numbers of output channels are used. This helps to condense and abstract the learned features, allowing the network to capture more meaningful information. And one of the important modifications is it uses a symmetric convolution layer, which also can reduce the calculation but achieve the same goal like before. And this is the details of the 3 modules. This is Inception A, Inception B, and Inception C. And this is 3 stages. Okay, then we talk about the auxiliary classifiers. These classifiers are attached to intermediate layers in the network and help to combat the problem of vanishing gradients. By including these auxiliary classifiers, the network encourages the propagation of gradients from higher layers to lower layers, facilitating better training and improve the overall performance. And the original model, like Inception v1, it used 2 auxiliary classifiers, but in our Inception v3, we use only 1 auxiliary classifier because we found that remove the classifier in the low level, this improvement didn't have an impact on the performance. Additionally, Inception v3 employs other techniques like batch normalization, which normalizes the inputs of each layer to reduce internal covariate shift and accelerate training. It also utilizes dropout regularization, which randomly disables a certain percentage of neurons during training, preventing overfitting. And in our project, we divide our datasets into 2 parts and 1 for train, 1 for test. We found that even classifying the CT scan, the Inception v3 model still can have a good performance.
Next is evaluation metrics. We use accuracy and F1 score to see the results. These are the formulas of 2 methods. Accuracy measures the percentage of correctly identified cases, and F1 score is the harmonic mean of precision and recall. Accuracy is used when the true positive and true negatives are more important, while F1 score is used when false negatives and false positives are crucial. Next is our results and analysis. These are the results of 3 different models. For VGG16 and Inception v3, we both run them 2 times, pre-trained and non-pre-trained respectively. First, we can see that VGG16 and Inception v3 have higher performance than HARLAC and AdaBoost. The reason is that HARLAC feature is determined manually, so it can only detect specific feature. If the data is tilted or part of the data is covered, it will have difficulty to recognize. However, the other 2 methods have higher degree of freedom, since it is determined by training, and it can recognize varying data. Second, we can see that pre-trained model is better than non-pre-trained model. It is reasonable because pre-trained model is trained on diverse datasets, allowing them to learn general features from the data. But non-pre-trained model doesn't, so it may need more approach to achieve same performance. Next is our limitation. CD images are not easily to obtain, so people may have difficulty to use our work. In addition, different types of data may have different results, like X-ray images, even they are the same part of human. And this is our reference, including our dataset, HARLAC feature paper, VGG16 and Inception v3. And here is our GitHub link. And this is the contribution of each member. And our final project report is in. Thanks for your listening.